So a lot of what we're doing today, you might have done everything we're going to do today in Algebra 1. All right, we're kind of going over measures of central tendency, which means mean, median, and mode, and spread, which is like range, right? And z-scores. All those things are kind of in Algebra 1 anyways, but they're also kind of important to normal distributions, which we're going to do next. So I thought we'd spend a day doing this. You'll probably think it's pretty easy anyways, but so by measures of central tendency, we mean mean, median, mode, right? So the mean is what we commonly refer to as average, right? You add up the values and you divide by how many values, right? Now, one thing we can do now that we probably couldn't have done in Algebra 1 is we can show this calculation, like I'm saying my 5 data values are x1, x2, x3, x4, and x5. So the mean would be x1 plus x2 plus x3 plus x4 plus x5 divided by 5. Well, now we've got the summation notation that we can use to represent that, right? The sum from I equals 1 to 5 of xi divided by 5. Okay, what is the median? How do you calculate median? It's the middle number, right? So if you have them in order, you throw out the high and the low, you throw out the high and the low until there's just one number in the middle, and that's the median. Now, on the data set that I'm showing in the bottom, 1, 2, 2, 3, 4, 5, if I throw out the high and the low, and the high and the low, I have 2 numbers in the middle. So then what is the median? It's the average of those 2 numbers, right? 2 plus 3 divided by 2, 2.5. And then what do we mean by the mode? Yeah, it's the number that occurs the most. So in this problem, what number occurs the most? 2. So the mode is 2. Now, what if my data set was like this? 1, 2, 2, 3, 4, 4, 5. Now what's the mode? Yeah, you would say that the mode equals 2 and 4. Okay, if in a data set like this, you say because it has one mode, it's called unimodal. Unimodal, right? If it has 2 modes, it's called bimodal. Right? So when we get to normal distributions next, I mean, a normal distribution is by definition, it's unimodal and symmetric. And we'll use that word, unimodal. That's what it means. You know, a normal distribution looks like, it's like a bell. Right? It's unimodal, it's got one peak in the middle, and then it's symmetric with respect to that. Okay. So these data sets give the waiting times in minutes of several people in 2 veterinary offices. Find the mean, median, and mode of each data set. So, calculator time. What did I do with my calculator? So, add them up. 14 plus 17 plus 18 plus 19 plus 24 plus 24 plus 30 plus 30. I'm getting 198 is the total, divided by how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 22. It was 198 divided by 9, which is 22. Okay, they're in order, so we should be able to tell the middle value is 20, right? So that's going to be 20. And the mode is 24. Okay. So let me do the next one. 8 plus 11 plus 12 plus 16 plus 18 plus 18 plus 18 plus 20 plus 23. 144 divided by 9. 16. Okay, what is the median? 2, 3, 4. The middle number is there, so that's 18. And the mode is 18. So based on the waiting times only, right, which veterinary office would you prefer to attend? Probably B. Looks like you're not going to have to wait as long. And there's other reasons to base the decision, but if that's the only thing. Now, when we talk about the mean, there's two ways that we refer to it. One is X bar, and the other one is with the Greek letter mu. It's pronounced mu. Right? When you hear them talk about mu alpha theta, that's the Math Honor Society. That's what they're saying, mu for that symbol right there. Now, they're actually not in statistics. If and when you take AP Statistics, you'll learn more about this. But let's say, for example, I wanted to find the average height of every student here at Tabb. How many students is that, more or less? Probably like 1,100, 1,200, something like that. So add up all the classes. I think it's over 1,000, for sure. Okay, now, do we want to go around and measure 1,100 kids' height? The answer is no. So in statistics, what you do, just like when they do these polls to see how people are going to vote, right? They don't ask 100% of the people. They actually take a sample, and they just ask the sample. Now, there is an average height. If you measured every kid in Tabb, there is an average height, right? And that average height is it's the average height for the population. And that would be mu, right? That's what this mu you use for the entire population that you're trying to assess, right? But when you take some kind of a subset population, I'll say the whole population. When you take a subset, like we figure out, well, let's come up with some kind of a sample which includes some 9th graders and some 10th graders and some 11th and some 12th and some girls and some boys, something we think is representative. And then we take the average. That average is actually an estimate of the population. We don't know if it's actually correct, but then you use X bar. X bar means this was the average of a sample. It's not necessarily the average of the whole population. This is sample. Now, the X bar, that's what you see in the calculator. But on the formula sheet, when they talk about the mean, they use mu, formula sheet. And honestly, there's really no attempt at distinguishing between population and sample means at all. It's just not the right level to do that. So we may use one a little bit inappropriately. But that's why there are the two, and we will see them both. I mean, they'll come up. We just have to, in our mind, to say, okay, that just means that's the mean. Right? Okay, so try to find the mean, median, and mode of that one. What do we get for a mean? 7.4. Median? 7.5. And mode is 8. Right. So sometimes in order to find the median, kind of helps to put them in order. So you can start throwing out the lowest and the highest, the lowest and the highest, and 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 what's left in the middle, 7 and 8, 7.5. Okay, measures of spread or dispersion. The book calls it dispersion, which is easily understood, but I think in like the AP Stats book, they always call it spread. So, spread is how much is the data spread out, and the most, the first one you ever learn is range. You've all learned about range before, right? That's the maximum minus the minimum value. The interquartile range, you did that one before, if you remember this, right? What's that called? That kind of diagram? Nobody? Box and whisker? Box and whisker, right? The box, these are the whiskers on the side. So the median is the middle of the box is, there's a line, that's the median, right? The minimum is the left whisker, the maximum is the right whisker. The median is the middle number, right? So that means 50% of the data should be to the left of the median, and 50% of the data should be to the right of the median. So if you find the median of the lower 50%, that's the left side of the box. That's either you can call it the first quartile or Q1. And the right side of the box is the median of the upper 50%. So that can be called the third quartile or Q3. So range, just the flat out range, the max minus the min, is not really a good measure of spread. Because for example, like if I go to the veterinarian and there are times where, mostly concentrated around 20 minutes. But let's say then the next time I go in, I wait 2 hours. I mean, that's going to make the range huge because of one value, which was anomalous. It really wasn't representative of everything else. That's why, as a better measure of the dispersion or the spread, we'll like to use how wide is the box, right? That's like saying, what is the width of the middle 50%? And that's called interquartile range, or IQR, which is just the Q3 minus the Q1. IQR, interquartile range. Right. And then there's standard deviation, which we'll talk about in a minute. But again, when you get into statistics mode, when you have a unimodal symmetric kind of distribution, then generally the mean and the median will kind of line up. And at that point, you want to use the mean for the measure of the center. And if you use the mean for the measure of the center, you always use the standard deviation as the measure of spread. If you don't have nice unimodal symmetric data, then you might use the median instead for the measure of the center. And then you would use IQR for the spread. I mean, they actually go together. You wouldn't use the mean and the IQR, or the median and the standard deviation, right? They kind of go together, those things. Okay, so we'll get to the standard deviation in a minute. That will be the highlight of your day. So we're going to find the range of waiting times in our vet offices, right? And these are already in order, so that's not a challenge, right? This one, the maximum is 32, the minimum is 14. I don't need a calculator for that. That is 18. Okay. For office B, 23 minus 8, which is 15. But I say my vet office is more like office A, and I think I think my mean is like probably 30 minutes. It is slow. They need an efficiency expert to go in there. So try to find the range of those. Everybody got it? Right. Not a hard concept. Okay. So standard deviation is the most commonly used measure of spread. So you look at these 3 data sets, and they all consist of 5 data values. The middle data set, well, first, they all have a mean. If you would add these up and divide by 5, they all have a mean of 3. They all have a median of 3. So you say, must be the same 5 numbers, but they're not. Obviously, they're different. Right? This middle one here, it doesn't have any spread. Every value is the same value. So if I was, what's the range of that value, of those values? 0, right? The max and the min are the same thing. It's just 3. And then between these two here, they both have 1, 3, and 5, 1, 3, and 5, but this one's got 2 and 4, and that one's got another 1 and a 5. So this one's got 2 values that are like a little further away from the middle than those two do. So if I was going to like rank order these, I would say probably the least standard, the least spread is there, the most spread is there, and that's the one in the middle. So sometimes the questions that we get about this are not actually calculate. It's more just trying to understand, what is it that it measures. If you just understand that part of it, if you got this kind of question on a test, like which is put in order of standard deviation, some measure of spread, they're not really asking you to do calculations. To just kind of look at it qualitatively and say, what's the order. But in any case, you would look at these, they have the same mean and the median, but they're clearly not the same data set. So now we're going to see this is how you actually do this calculation. Did anybody do this calculation before, like in Algebra 1? To actually longhand calculate a standard deviation? It's on the formula sheet, which kind of implies that they expect that you would use the formula to do that, but nobody ever does that, okay? Nobody does that. But we're going to do it. So you can say one time in your life that you did this, okay? So try to imagine that you wanted to come up with some quantitative measure of how much data is spread out, right? What's the deviation between the data values and the measure of the center? So just taking 5 simple numbers there. The mean is 1 plus 2 plus 3 plus 4 plus 5 divided by 5, which is 3. So if I want to know like how different is the data from the mean, the first most logical thing to do is, well, let's just subtract, right? Let's take x minus the x bar, the mean, for the 5 values. And we would get 1 minus 3 for the first is negative 2, 2 minus 3 is negative 1, 3 minus 3 is 0, 4 minus 3, 5 minus 3. There's the 5 differences from our data values and the mean. Okay, now but I need to know like what is the spread of the whole set. So what if I just added them up? And I'm going to use the summation notation. The sum from 1 to 5 of xi minus x bar would be to add these 5 up. And what would you get? You would get the negative 2 canceling with the positive 2, the negative 1 canceling with the positive 1, and you get a sum of 0. Does that mean there's no spread? Well, that is kind of what it seems like. So obviously we can't just add up the differences. So what we do is, well, let's square the differences, right? What will this squaring the differences do right? It's going to make all of them positive, okay? Now, that's not the only option that you've got. Does anybody think of another way you could get rid of negative signs? You could take absolute value, right? And that was another formula on the Algebra 1 formula sheet, mean absolute deviation instead of standard deviation. But that's not even though that's a totally valid kind of way to calculate dispersion, it's not usually used. And the reason is because standard deviation, as complicated as this formula, all this calculations look, it actually is exactly part of the normal distribution. So it really fits in. We need to have this measure of spread. So, okay, so we jump down to this here. We say, okay, let's square all those differences. So -2 turns into +4, and -1 into +1. And when we add them all up, we get a +10. All right. So then we say, well, that's great. That's the sum of those deviations, but we want an average. So let's divide by 5. And when we do that, we're going to get 10 divided by 5, 2. But if you look at our numbers here, actually the biggest deviation from any data value was 2. That can't be the average. That can't be some measure of the expected deviation, because actually we had a 2 and a 2 and 1 and a 1 and a 0. Okay, so what we do is the last step is after you've done this, you've summed up the squares, you've divided by the number of terms, then you take the square root, right? We squared over here, so now we take the square root. So this is the calculation, right? The square root of the sum from 1 to 5 of xi minus x bar squared divided by 5. And so that means for us, take the square root of 2, and that's 1.4. That's standard deviation. And actually, this number right here, before you take the square root, that's called variance. The average of the sum of the squares is called variance. And that's also used in statistics, and that was actually also on the Algebra 1 formula sheet. Right? This is called variance. And in statistics, like in a higher class than this, sometimes you use variance. So this is the formula for standard deviation. And the symbol we use to represent it is a lowercase Greek letter sigma. So like in the formula, we're using the capital letter sigma for summation, and then we're defining it with the lowercase letter sigma. That's standard deviation. Again, we're kind of playing fast and loose here with this stuff, because sigma is usually what you use when you're talking about the population standard deviation, and x bar is the mean of the sample. So we're kind of mixing apples and oranges here, but we won't worry about it at this point. The standard deviation for a sample, you use S. You don't use sigma, you use S. Okay. So we're going to do a couple calculations. So there's my numbers. I think these were our waiting times of veterinary office A. So first I'm going to find the mean was 22, already calculated. I'm going to take our differences. So 14 minus 22, negative 8. 17 minus 22, negative 5. 18, negative 4. 19, negative 3. Negative 2. Positive 2. Positive 2. Positive 8. Positive 10. Right, so those are the differences. Square them all. 64, 25, 16, 9, 4, 4, 4, 64, 100. Okay, next, add them up. 64 plus 25 plus 16 plus 9 plus 4 plus 4 plus 4 plus 64 plus 100. And I'm getting 290. Okay. Now we need to divide that by, how many was that? 1, 2, 3, 4, 5, 6, 7. It was 9. Does that look right? 4, 5. Yes. So that'll be 290 divided by, I should wrote that as a 9. .2 repeating. Right, that's the variance, and then the standard deviation will be the square root of that. Second square root. 5.67, how about call it 5.7. So another reason for taking square root is that you're trying to come up with some measure of how spread out the data is. But you know, the waiting times at the office are all measured in terms of minutes. And at this point here, you're taking the sum of the squares. This is minutes squared. By taking the square root, you're getting back to a measure of spread which is in the same units as you're measuring, right? 5.7 minutes. I mean, in the end, that wasn't that hard of a calculation. You just take it one step at a time. Okay, so here's your U try to do it with a little harder data. Right? So this was the waiting times of the bus for 10 students, so there's 10 values there. I think we already did the mean. The mean was 7.4. So try to do the one step at a time, right? First do the differences, then square them, then add them up, then divide by 10, then take the square root. So what did you get when you added them all up the sum of the squares? Say again? 138. Man, I'm way off. Okay, let's make sure we got these right. 11.56, 0.36, 21.16, 57.76, 19.36, 29.16, 1.96. The 1.6 I've forgotten. I had to go back. That's 2.56. Then I get 0.6, 0.36, and 0.16. All those are okay? So, say again? 144.4. I must have forgotten one number in there. Clear. So let me erase that. There's my doc. So get rid of that. So you're saying 144.4. Okay. Oh, sorry, that's not even right. That goes here, 144.4. Right, and then you divide by 10, 14.44. Then you take the square root. 3.8. Well, so the whole point of that is you don't want to have to be doing that by hand, right? You can do this actually with the calculator. Right? So the way you do it is like this. In fact, let's do it with that same old data set that we just used. So the first, let me change my doc bottom. So first you go to stat edit, and clear out your list. Remember how to clear them out? Go to the top, clear, enter. Go to the top, clear, enter. Okay, and now you're going to enter in your data values. Let me go back to there. So 4, 8, 12, 4, 8, 12, 15, 3, 2, 6, 9, 8, 7. That's 10 values, right? So go back. So stat edit, put all the values under L1. It's just one list of numbers. Okay, next you do stat calc 1 for one variable stats. And it's drawing the list from L1. Enter, enter, enter. So what you see, right? You see the X bar, 7.4. You see the sum of the values and the sum of the squares. That's not the sum of the differences of the squares like we did. And then you see this sigma X right there. That's the standard deviation, 3.8. So actually on this screen, the only two numbers you're going to look at are the X bar and the sigma X. That's the mean, that's the standard deviation. That's actually, this SX, that's actually a standard deviation too, but that's the one it's only of a sample, not of a population. And the difference is like this, you know, when you're trying to measure the ways that data can vary, when you do the calculation for the standard deviation, if you calculated, well, just take it back to, you don't have to do the whole calculation, but let's take it to one that was pretty clean, right? So when I take a data set like this and I calculate the mean, okay, and then I do all these differences, I'm doing this calculation here. The fact is that every time I do this subtraction here, I'm using a value that was actually calculated by taking the average of all those numbers. So in the end, when I'm doing this subtraction, like how much the first data value varies from the mean, okay, that's a way that this could, it adds to the variability, let's say. And with the second and the third and the fourth, all the way up to the ninth, then without even knowing what that last value is, if I know what the first 9 values are, and I know all of these differences, which were all calculated using the mean, which was the sum of all those, actually that last value has to be what it is. And so the data really can't vary in 10 different ways. It could only vary in 9 different ways. And that's called degrees of freedom in statistics. And for that reason, that's why you've got this number right here. This is what you would have gotten if you divided by 9, not 10. This is the one you get if you use a sample mean to calculate the standard deviation. Then you got to use n minus 1, not n, right? If you're going to use something like 3.8 and just assume it's the population mean, then you get our standard deviation. That is the one that we use. But in statistics, a lot of time you use that. And I remember the story of where that came up, because they used to just always calculate standard deviation and think that was fine. But it was this guy that was working at the Guinness brewery in Scotland or wherever it is. And he's the one who discovered that, you know what, this thing is not, it's not accurate. This number that we're using in our calculations is leading to wrong assumptions, like in how many bad samples should we draw in 100? It wasn't coming up right. And then he came up with the idea, you know what, because it actually can't vary in that many ways. So the standard deviation was higher than they thought. So now if you scroll down, right, if you scroll down from that screen right there, you see that it's also got the min and the max and the median And the Q1 and the Q3, all the things that we'd use to make a box and whisker plot are right there. Okay, we probably don't want to know all of them, but a lot of times we'd like to know the median. So it'll actually do the median for you right there. It doesn't do the mode, but in the one calculation, you know, it does the median and it does the mean, and it does standard deviation. So let's try. Okay, one last thing. No, actually, two things. When one data value is much different than the rest, that's called an outlier. And usually, if there's an outlier in the data, let's say my 2 hours waiting at the vet office when all the rest of the times are only 20 minutes, usually you would calculate the statistics with the outlier and without the outlier. I would say that usually it's the outlier. As much as knowing the mean and standard deviation, it's the outlier from which you will probably get a lot of, you know, understanding of your processes. And I mean, my bet is that a fair number of you someday in your careers will have to stand in front of a group of people with data on the screen and talk about the data that's on the screen. And the one value they're going to be looking at is going to be the outlier. You know, they see all these other most of the numbers are all the same, and then they see this one that's like not the same. You know, which one of these things is not like the other? That's the one they're going to want to know. You don't just like brief, oh, well, here's the mean and the standard deviation. Next slide, somebody's going to say, wait a minute, go back, talk about the outlier. So there's a very good book called Outliers by an author named Malcolm Gladwell. And it's talking about people that we consider to be like outliers, people like Bill Gates, let's say. And it talks about how they became that kind of person. In most cases, it wasn't just that they were born that way. They actually worked really, really, really hard to become the way they are. Like in computer programming, they said, generally, well, not just in computer programming, they say, in order to become a genius at doing something, you generally need like about 10,000 hours of working on that skill to do that. And if you figure, like, from the time somebody like Bill Gates, from his teenage years, go into this library that first had computers that he could sit down and work on, and how many hours he put in? He probably put in 10,000 hours. Or if you look at people that are like really virtuoso musicians or something like that, they probably have put in something like 10,000 hours to become that good. You know, we tend to think of them as just like geniuses that, oh my gosh, you know, they were just born this way, but they weren't necessarily born that way. And it was an interesting book. They had another interesting one, right? I think it was in that book. He has 4 books that I've read. But he was talking about, do you know that if you look in the rosters of the National Hockey League, that by far the most players' birthdays fall in January and February. Now, why would that be? Why would only people from January and February be the ones? And so the explanation is that, you know, from a young age, I mean, you go in Canada, where most of these players come from, hockey is like a religion. They do this by the time they can walk, they're probably put on ice skates, and they're ice skating. And playing hockey is a really big deal. So the cutoff to get into like one league or the other by age is December 31st. So like if you're born on December 31st, you get in that group. If you're born on January 1st, you got to wait a year. So you could be practically a year older than most of the kids that you're playing with, right? Now, when you're 5 years old, being 1 year older makes a big difference. And they stand out. And then when the next level is looking for the best players to, you know, bring to the next level or give special training and coaching, they're always end up picking these kids that are the ones that were, you know, the January and February ones that were actually almost a year older than some of their teammates. And the same thing happens, they showed in like European soccer, where the cutoff is like July 31st. So a lot of players, a disproportionate number of players come from August and September birthdays. So, but that's a book called Outliers. those books are very interesting. You guys, I mean, if you had to read a short, interesting book for a project or something, any one of those books would be really, really good. Blink is a really good one. The Tipping Point. Anyways. So let's say here's another set of data. It says you're competing in an air hockey tournament. The winning scores for the first 10 games are, and there's the 10 scores. Okay, the winning score for the next game is 3. So here's all these values, the least of which was 11. And now you have one value which is 3. That would be considered to be an outlier. So let's calculate the mean and the standard deviation, but we'll do it for both. We'll do it without and we'll do it with the outlier. So I'm going to make a little table, and we could definitely do it with the calculator. We're not doing this by hand, right? So this is with, or this will be the mean. I'll use X bar, and this will be sigma, and this will be the with out first, and this will be with the outlier, right? So, and I'm just going to do it in front of you right here. So stat, edit, clear the list, and 14, 15, 15, 17, 11, 15, 13, 12, 15, 13. So that's how many values? That's 10. So that's good. So I'm going to calculate stat calc 1 and enter, enter, enter. So it looks like the mean is 14 and the standard deviation is 1.67. Okay, then I'll go back to my list and I'm just going to add the one value. Go to the bottom and put a 3. Okay, stat calc 1, enter, enter, enter. 13 and 3.54. So, I mean, the reason I threw that on there is because the homework problems I'm going to give you in the book, they ask for that. So I just wanted you to know that's what they mean by outlier. And then the one more topic, which is short and sweet, which is z-scores. Right. Z-scores are in Algebra 1, but they're actually on our formula sheet too. Although I've never seen them asked, I'm not sure they've asked a question on a released SOL on z-score. But z-scores are part of normal distributions, so it's not a bad thing to review what it is. Right. So we should recognize the z-score is the thing we're defining here. The z-score is the number of standard deviations from the mean for one data value, right? The one data value is that one, right? We know what the mu is, right? That's the mean. And we know what that sigma is, that's the standard deviation. So do a couple calculations with that. 25 students in a chemistry class take a test. The mean score is 80 with a standard deviation of 5. You scored 90. What is your z-score? So use the formula z equals x minus mu divided by sigma. All right. So in this case, the x is 90, the mean is 80, and the standard deviation is 5. So that's 10 over 5, which is 2. So you scored 2 standard deviations above the mean. And yes, you can get negative standard deviations, right, if you score below the mean. Okay, in a different group of 25 students, in a math analysis class, the average test score is 75% with a standard deviation of 3. You scored 84. What is your z-score? So z equals 84 minus 75 divided by 3, which is 9 over 3, which is 3. All right, so now you scored 3 standard deviations above the mean. So on which test was your performance better compared to the rest of the class? For the math analysis, you were 3 standard deviations above the mean. You know, generally speaking in statistics, when you're more than 2 standard deviations from the mean, that is considered to be unusual. That's considered to be something that's, you know, for example, if you are, you know, doing some kind of drug testing or something like that, and you're measuring, you know, somebody's wellness or something, in whatever way you measure it, if you go out and do a sample, like you give that drug to a bunch of people, and then you measure them, and they end up being more than 2 standard deviations from the mean, that's statistically significant. If it ended up being like 1 more than the mean, they would say that's not statistically significant. It may be a little bit better, but it's not better enough for us to throw away what we thought we knew up to then. Okay. Now, you know, you would probably rather get a 80%, or sorry, a 90% than an 84 on a test. Because in the end, you're kind of measuring the same kind of thing. But where this can come into play, especially, it's like if you're trying to measure things that are on completely different scales and try to figure out like which is a better performance. Like, for example, in the Olympics, you know, you could have a hurdler who's running, and you want to know, like, was his performance better than the shot putter, right? Well, this could, by just calculate the mean and the standard deviation, you can calculate a z-score and see which performance was further from the mean, more standard deviations from the mean. That's the one you want to go with. Of course, now, if you're measuring a hurdler who's running a time which the best is faster, you know, you want to be below the mean there. If you're a shot putter throwing for distance, you would actually like to be above the mean. So you'd have to take that into account. All right. So that's it. So I only gave you 2 problems from the book, and those are just calculate mean and standard deviation with and without an outlier. And then I'm going to give you a z-scores worksheet. Something to practice, because the book doesn't really have any z-scores problems. Okay, finito.